This conference will now be recorded.
So very good evening, students. Today we'll discuss questions from JEE Advanced paper on magnetics as well as electromagnetic induction. So let us solve these problems. I have few problems today to solve on this magnetics as well as electromagnetic induction. So here there will be chapters 4 to 6, because some of the questions, as I mentioned in the previous class, it is really difficult to distinguish like whether it is from magnetics or it is from electromagnetic induction. So in advanced questions you have concepts from all the chapters together. Okay, let us see this problem. A long straight wire carries a current I is equal to 2 ampere. You look this is the long straight wire. It carries a current 2 ampere. A semicircular conducting wire is placed beside it. See, a semicircular conducting wire is placed beside it on two conducting parallel rails of negligible resistance. So these are rails. Okay, this is one rail and this is another rail on which a semicircular conducting rod, this is conducting rod is kept. And rail means, you know, this is movable, so this can be moved this way or this way. Okay, so this is the situation here. So this is the wire which is carrying, this is a long straight wire. That means you can use Ampere's circuital law to calculate the magnetic field produced by this current at any distance. Okay, and these are the rails. As I said, these are parallel rails. So first rail is 1 centimeter away from the wire, or you can say the first end of the rod is 1 centimeter from the conducting wire, and the second end or the other end is at 4 centimeter away from the wire. So that is the information here. Both the rails are parallel to the wire. Both the rails are parallel to the wire. The wire, the rod and the rail, this all actually lie in the same horizontal plane as shown in the figure. As you see, two ends of the semicircular rod at a distance 1 centimeter and 4 centimeter from the wire. At time t is equal to 0, the rod starts moving on the rail with speed 3 meter per second, as you see here. So at t is equal to 0, it starts moving, okay, with velocity 3 meter per second. A resistor 1.4 ohm and a capacitor C0 is equal to 5.0 microfarad are connected in series between rails. See this R and C0 or CO, you can say C0. So this is a resistor, this is a capacitor. Initially the capacitor is uncharged, it is given somewhere, we'll see that. So these two are RC in series connected with the ends of the rod. Okay, connected in series with the rails. That means this connected. So this is a complete circuit, you can say that this is a complete circuit. So if there is see this rod is moving, right? So you can see this is a closed loop. Now this portion is a closed loop now. Okay, closed loop. Now if the loop area changes, see magnetic field will be fixed magnetic field will be produced by this wire in this region. Okay, now if this rod is moving, then there will be change in the area, change in the area. So because of that, Because of that, there will be EMF induced. This is called motional EMF. This is called motional EMF, and motional EMF generally calculated with the formula BVL, where V is the velocity, L is the length of the rod, and this is, if this is a rod, this is L. So suppose this is a rod of length L, and it is moving with velocity V, and magnetic field is there inside. Okay, so BVL, so BVL is the formula. Okay, but this is the general formula. Okay, and most general formula will write here. Okay, let us see the questions. So at t is equal to 0, C0 is uncharged. That means this capacitor is uncharged at t is equal to 0 when just this rod started moving. Which of the following statement is or are correct? Where mu0 is given in SI unit, and ln2 has been taken as 0.7. Okay, generally it is actually 0.693, something like that. So that has to be taken as 0.7 for the calculation purpose here. So this is the whole problem. See, the question is the maximum current through R. So what is the maximum current flowing through R? See, if we know the EMF developed across this, okay, EMF developed across these ends of the, or across the two rails, then we can just find out. So if this is E0 by R, that will be giving you maximum current through that. Okay, now we can check that only when we will be able to find out this potential difference or potential or EMF developed across these two rails. So that we have to find out. So that is the main motto over here. So we have to find out what is EMF to answer whether these two, like among these two, which one is correct. And then last two options are related to charge on the capacitor. Look, the charge, the maximum charge on the capacitor C0 can be written as CV. You know that V is the potential difference between the plates. So if the potential difference in this case EMF across the R, so potential difference is EMF across these rails. If we can find out that, then we will be able to find out maximum charges as well. So main thing is here that you have to find out EMF, motional EMF. So how to find out motional EMF? You look, I can just consider see the elemental EMF. Let me consider elemental EMF. So, see, I can just take any element over here, right? So this, we have to find out the area of this. So if I take an element, then we can write B anyway constant always, velocity is constant, BV, and the thickness, let us say this is dr, BVL, right? BVL, so BVdr, like that if we just take, okay, BVdr, right? So then we will be able to find out. If we integrate it, see, EMF will be integration. See, this L actually starts from here, not only inside this. I think I have to take the area region over here. Okay, not only that, because the wire is here, so the rod is here, so here also magnetic field will be there. So the flux actually starts from here to here, and that flux, okay, so changing the flux we have to find out, right? So it is dr, so R is equal to, or L is equal to, I could just write here dl also. So here the limit is 1 to 2, sorry, 1 to 4, this limit 1 to 4, dr has a limit 1 to 4. That means this is the distance, actually distance from the wire. Okay, bvl, this length. Okay, so bvl, and dr. So what is b here? At distance r, so at distance r I have taken dr. At distance r, b will be mu 0 I by 2 pi r, right? So this is the magnetic field, right? So mu 0 I by 2 pi r. So I can write it here in place of b. Okay, we'll just do here. So E will be integration r is equal to 1 to 4, and it is, so b is actually mu 0 I by twice pi r v and dr. So mu 0 I v will be as it is 2 pi. I'll take it out, and v also will come. So here dr by r, right? And it is limit of r is r 1 to 4. Okay, so this is mu 0 v I divided by 2 pi and ln r, limit 1 to 4. So ln 1 is equal to 0. So it is actually mu 0 v I by 2 pi into ln 4. So this 4 can be even written as 2 square because ln 2 we know the value is given for calculation. So vi by 2 pi. So this 2 can be written here. So 2, this is 2 pi and this is ln 2, right? So mu 0 vi by pi ln 2. For the calculation sake, we have to put the value. I is 2 ampere, right? So this will be in volt if we put all in SI unit. So mu 0 is 4 pi into 10 to the power minus 7 SI unit, and V is 3 meter per second, and I is 2 ampere, and here in the denominator pi will be there, and this is 0.7 according to given. Yeah, it was given ln2 has to be taken as 0.7. Okay, this pi goes off. You can see this is actually 24 into 7. We can just, okay, let me just skip this itself because I have seen there is, okay, let me just skip this. So this is 24 into 0.7 whole to the power 10 to the power minus 7. Okay, or we can just keep this as 24 into 7 into 10 to the power 8. This is actually volt EMF. Okay, once we get EMF, let me just check first one thing. Do I have? No, I don't have any space here. So I'll just calculate Imax. As I was saying, Imax can be written as E by R. So what is E? E we have found out 24 into 7 into 10 to the power minus 8 divided by R. What is the value of R? R is given as 1.4 ohm, 1.4 ohm, and this is, okay, so 1.4 ohm. This is the thing. Now look, this will be, so this is 10 to the power minus 1. So if this goes here, so it will be 10 to the power minus 7. So this will be 2. So 12 into 10 to the power minus 7. Okay, 10 to the power minus 7. This is the amp. This is in ampere. We'll see. Okay, 10 to the power 6. We can write it as 10 to the power 6. Okay, 1.2 into 10 to the power 6 ampere. Look this. The maximum current through R will be this much. Okay, so the first option will be the correct option over here. Let us see among these two. So current, regarding current we have obtained already. We'll see regarding charges. As I mentioned, charge is actually see I have got the EMF. Let me, so EMF we have obtained 224.7 into 10 to the power minus 8 volt. Current we have found out maximum current as 1.2 into 10 to the power minus 6 ampere, and we have these values given. CO we have to find out. What is CO? We have to find out. The capacitor, sorry, not CO, the charge on the capacitor. So this is 0.5 microfarad, 10 to the power minus 6 farad. So microfarad, C0 is given already. Sorry, this is 50. 5, not 0.5. This is 5. Okay, 5. So now, if you want to find out the maximum charge on the capacitor, then C0E. Okay, C0 is 5 into 10 to the power minus 6 farad into E is 24.7 into 10 to the power minus 8 coulomb. Okay, or look, this will give you 120 into this 10 to the power minus 14, right? So it is in coulomb. So 8.4 into 10 to the power minus 12 coulomb. Okay, I hope it is all right. Yes. So 8.4. So C, option C is correct answer for this question, and this D is not the correct option. Okay. So this is how we have to solve the problem. So here, what was the main point? Main point, how do you calculate EMF here? So you apply BVL, but L is not a constant here. See, you can just take, you have to do the integration part here. So that is BVDR, and DR, actually R goes from here. So 0 to 5 or 1 to 4. Actually, that is the real advantages. Okay, so that you can do. So this is how you have to solve this problem. We'll go to the next problem. This is from magnetics. Okay, so you can see there is XY plane. Okay, X and Y. So this is the XY plane. Okay, has a uniform magnetic field B1K in the region Y is equal Y greater than 0. That means positive side. If this is Y axis, so this region, and this is X axis. So this region, and this is actually Y less than 0, right? Negative Y, and this is positive Y. Y greater than 0 is this region, whole region is Y greater than 0. So here there is uniform magnetic field B1K cap. That means magnetic field is always pointing in the Z direction, and there is a constant value of magnetic field B1. Okay, and the region Y less than 0, that means this region, negative Y axis. This region has another uniform magnetic field B2K here. Another uniform magnetic field. A positively charged particle is projected from the region along the positive y-axis with speed v is equal to pi meter per second. Okay, I hope this is correct. Okay, pi meter per second at t is equal to 0 as shown in the figure. So you can see that initially at t is equal to 0, the particle is thrown along y-axis with the velocity v0 is equal to pi meter per second. Okay, now the thing is, neglecting the gravity because it is a vertical axis. Okay, we can neglect that. So you know this is z direction. Okay, somehow neglecting the gravity in this problem, let t small t be capital T. Small t be capital T. The time, it is the time when the particle crosses the x-axis. At t, it crosses the x-axis. below for the first time. Okay, for the first time you can see for the first time, neglect the gravity in this problem. Okay, all right. So if the b2 is equal to 4b1, the average speed of the particle in meter per second along x-axis will be how much? Okay, in the time interval t, capital T. All right, we'll just solve this problem. First of all, you look this whenever see this magnetic field is along the z direction and this is y direction. So velocity and magnetic field, they are perpendicular to each other. For a charged particle having charge, I think this is a positively charged particle. Okay, positively charged particle q. So whenever the magnetic field and the velocity of the charged particle is perpendicular to each other, so there will be a trajectory of circle. Okay, so the path of the path of the charged particle in along which it will move will be a circle. Okay, will be a circle as you see. So it starts from here and it will come like this. Okay, and you can see the magnetic field B, magnetic field. Okay, so magnetic field B1 and B2, there are different magnetic fields. This is B1 and this is B2. And you know, the centripetal force mv square by r will be, if I say this is R1, so this is actually supplied by BQV. So B1, Q is the charge say, and B0, right? So if we type, okay, B and B0 are same actually. So we have to find out mv by r. So we have to find out r. R1 will be actually mv by B1Q. So the radius will be always inversely proportional to the magnetic field. Inversely proportional to the magnetic field. Okay, so it will be, since the magnetic field is 4 times for the other case, okay, in the region y less than 0, that means in the negative region. So this B2 is actually 4 times greater than B1. Okay, so that's why when it comes here at time t is equal to t, it reaches here and then it enters into the region of magnetic field B2, which is a strong magnetic field. And you look, this radius of the circular path will be inversely proportional to magnetic field. That's why it will have a small radius compared to the radius of this. So that's how you get two actually semicircular arc. You will get two semicircular part. You will get one starts from here and come to here, which is radius r1, and another semicircle we will get as this one, as you see this one, and it has radius r2. So radii will be actually different. All right, with this you can see here the question is, what is the average speed? So average speed, we know average speed will be the total distance covered divided by total time interval, right? Total time. Okay, so it is the interval t, capital T. So that time is fine. Now you have to find out what is the distance. See, the distance is actually from, see, this is actually d, how much it goes. Distance you have to find out. Average speed, not the velocity, average speed. So total distance, not the displacement. So total distance means, see, this much it goes fast. So let us say this is d1, and then it comes back to this much. Okay, so this is d2 say. Okay, d1 and d2 we can find out. So 2r1 is d1. Okay, and d2 will be 2r2. That's fine, right? These are the distances, right? So we have to find out what is r1 and what is r2. Now let us say, so bqb, as I said, so I can write r is equal to mv by qb, right? mv by qb. So if I write r1 here, it will be this. Charge and mass, they are same. Velocity also is same. Okay, velocity is constant velocity, that is that is pi meter per second, pi meter per second. Okay, and then R2 will be m v by q v2, right? So this part, you look, it is actually the same. This part is same for both. Then I can write actually, see, in place of this I can write v1 into q, v1 into q, v2 into q, v2 into q. So this is fine. I can see that b, again I have to find out R2, right? So again b2 is actually 4b1. So this is b1 and this is, okay, I'm sorry, this is b1r. This will not be there because I'm just putting the value, this much value, b1r1, b1r1. So b1, let us keep that as it is, and b2 is 4 b1. So b1 goes off. So r1 is actually 4 times of r2. Okay, this is the relation we got. Now the question is, what is the total distance? So total distance is d1 plus d2. Okay, what is d1? The d1 is 2r1 and d2 is 2r2, as I showed you. So this is actually equal to, this is equal to 2r1 is, let us keep that as r1 plus 2r2. R2 is again, okay, R1 is 2r2, 4r2. R1 is 4r2. So R2 will be R1 by 4. So it is R1 by 2 into R1 by 4. That means this R1 by 2. So it is actually, look how much it is, 5 by 2 R1. Okay, 5 by 2 R1. All right, let us see. Now what is the T? We'll find out in terms of R1. T is the time when it actually reaches here. Okay, that means it is actually, see, time period, see, this is a constant velocity anyway. So pi r divided by pi r1 divided by velocity pi. Okay, it will be actually r1. The question was what is the average velocity? So what was the question? Question was, what is average velocity? We'll see how much it is. So this is actually, T is actually, okay, this is pi, yes, pi r divided by velocity is pi, right? 5 meter per second. So it is r1 alone. So I'm getting here T is equal to only r1. So the velocity average speed is 5 by 2 r1 divided by T, that is r1. So it is actually 5 by 2. Okay. So the question was, in the xy plane, the region y greater than 0 has uniform magnetic field V1K. So let me just check. Average speed it actually the answer should be 2. We have done some mistake, maybe. Let me just check what was the mistake. Okay, anyway, method is the same. We have to find out the time. So it took, I think it is here, right? There will be 2 times. Okay, this is not only this. Okay, so let me check what is the time. It goes here up to this. This is R1. And what about this? This is actually, if I say this is T2, that T2 is actually again pi R2 divided by the speed divided by the speed pi. So this is actually R2, right? So this is R2. So the total time will be actually T1 plus this is T1, say this is T1, this is T1, and this is T2. T1 plus T2. So T1, so R1 plus R2. What was the relation between R1 and R2? We had seen that R1 was 4R2. Okay, this was the relation because R1 is greater. That we have found out, right? This is R2. Look, B1 is, sorry, B2 is 4, B1. R is QM, sorry. This is BQV. BQV is equal to MV square by R. So R will be MV by QB, right? MV by QB. So R1 will be this, V is same, M is same, and R2 will be MV by QB2. That means B2 again it is actually MV by B2 is actually 4R1, B1. So it is actually 1/4 of R1. So this is what I said. So R2 and R1. So we get total time T1 plus T2 is equal to R1 plus R2. Okay, so R1 is anyway, this is 4R, sorry, R1 is all right, R1 is R1, and R2 is R1 by 4. So this is actually 5 by 4 R1. Okay, this is the time. I think this is where we had done some mistake. Other things were all right. What we have found out? We have found out the distance, and total distance was 2 R1 plus R2. So this is the one it was. So see, total distance here. So it is 2 into 5 by 4 R1. So it is 5 by 2 R1. Now see, we have average speed d by total t. D is 5 by 2 R1 and t is actually 5 by 4. So 4 by 5 R1. Okay. So this R1 goes off. Okay. 5 we can strike them out. So it will be actually 2 meter per second. It is the answer actually. Okay. So this is the answer. We'll go to the next problem. So this problem is really interesting problem, as you see. A conducting wire, this is actually from electromagnetic induction, a conducting wire of parabolic shape. You can see that, conducting wire of parabolic shape. Initially, y is equal to x square is moving with the velocity v is equal to v0 I cap. That means it is moving in this direction. The wire is moving actually in this direction. Okay. The magnetic field is this. This magnetic field is not an uniform magnetic field, not a uniform. This is non-uniform magnetic field. B is equal to, since B is equal to B0, it is heading as B0. Actually, this is along K cap direction. Okay, K cap. B0 1 plus Y by L whole to the power beta K cap. Okay, this is what is the magnetic field. Now you have to find out, see, V is along Y direction, sorry, X direction, B is along K direction, so B, and L is along Y direction. You can see that. So Y is equal to X square. Okay, so you can actually apply formula, BVL formula if you want to calculate the EMF. Okay, so how to do that we'll see. So if you like, you can just use the BVL formula, but how to use that formula, you have to be careful about it. Okay, so now as shown in the figure, okay, so a conducting wire of parabolic shape, initially y is equal to x square is moving with b is equal to v0 I cap in a non-uniform magnetic field. B is equal to v0 1 plus y by L whole to the power beta K cap. As shown in the figure, if V0, B0, L and beta are positive constants and delta phi is the potential difference developed across the ends of the wire, then the correct statement is or are. So there could be multiple answer correct. We'll see which are the correct option here. See, the option is the delta phi is directly proportional to the length of the wire projected in the y axis, projected in the y axis. So it is actually parabolic conducting wire. Okay, so if we project in the y square, so this is the L, length of length, whether it is proportional to L. So delta phi remains same if the parallel wire is replaced by a straight wire. Y is equal to x initially. Y is equal to x. See, or of length to L. See, if this is y is equal to x. Okay, this is y is equal to x line. Y is equal to x line is this one. I can just remove this. Yes, let me just draw the solid line. This is y is equal to x. Okay, y is equal to x. It says the flux delta phi, change in the flux delta phi will remain the same. We'll see how much correct it is. And C, option C says when beta is zero, then delta phi will be this much change in the flux, and when delta phi is beta is equal to 2, delta phi will be this much. All right, so we have to first of all see, you have to find out delta phi. So all the questions are related to delta phi or the change in the flux. So how to find out change in the flux? As I said in the previous problem also, look, this is nothing but BVL. So BVL, this is the formula, motion and EMF, BVL. But see, sometimes this L is not a straight line. Okay, not a straight line, neither it is. So you have to actually take some time, see magnetic field in such a way that for calculating the motion and EMF across the length of the wire, let us project the wire such that B, V and L becomes mutually perpendicular. L becomes mutually perpendicular. We are just projecting this, okay, in this way. perpendicular. BV and L becomes mutually perpendicular. Okay. Thus, we can actually write delta E is equal to, see, we can just take an element. So if this is the wire of length L, we are just taking the projection of that. Okay, we have just projected the length of the wire as L. The total length is L. So this is the projection, and we take at a distance Y. Let us take the element of the length dy of thickness, or small element of length dy at a distance Y from this x is equal to 0. So we can write B anyway. B is not constant, so we'll just integrate it if required. But in this case, actually, the integration will be on dy alone. Okay, B, then V, that is constant actually, B V0, and dy, that is the length which is changing. So this is the parameter which is changing in this case. Okay, and also you can see B, which is actually not a constant. This is also changing in the direction, like changing with L only, y by L beta. What is the word beta? So this is changing along the y direction. Along the y direction it is changing. Okay, magnetic field is changing along the y direction. So this is the variation we can see. So this variation will be taking care of the variation of magnetic field also here. So let us write B0, and this part will be inside the integration. And what is the limit of integration? If we want to find out what is the total magnetic field, sorry, magnetic EMF, total EMF developed across this, like at the ends of the wire, that is, see, integration 0 to L. Okay, y will be 0 to L, because we have taken this L is equal to 0 here, and here, sorry, y is equal to 0 there, and y is equal to L here. Projection of this wire. So dy is B0, V0. These are constant term, and then we can write 1 plus y by L into dy. Dy is actually will take care of this thing. Okay, BV, and this is the limit. Okay, so this is the limit. Now you can do the integration. You can do the integration part over here, and with respect to y, or see dy y, right? So this integration will be B0, V0. If we take L common, then it is, see, it is y. See, it is actually, we have to do the integration part only on this L to the power beta. Okay, beta will be L to the power beta here, and dy. That means beta will be beta plus 1 will be down. So 1 plus here, beta plus 1, and here it will be y, beta to the power y to the power beta plus 1, and that limit is L to the power beta plus 1, right? So that beta we have already taken out, right? We have taken out. So it was like this, L to the power beta plus 1 divided by L. So what we have taken? We have taken L into beta L to the power beta divided by L. So, and when L is equal to 0, L is equal to 0, y is equal to L, and L is equal to 0. So there are two things. So people just, okay, let me just do it, or we can write it. Let me first write it, and then I'll tell you how we come here. B V0 B0 V0 L 1 plus 1 over beta plus 1. Let me do this integration somewhere else. B0 1 plus y by L whole to the power beta, right? And this is with respect to dy. Let this be here 0 to L. So this is y, which has limit 0 to L, and this is y to the power beta plus 1 divided by beta plus 1 and whole to the power L to the power beta. It was there, and this is limit 0 to L. Now let us see y has limit L, lower limit 0 here, and upper limit if we take y is equal to L to the power beta plus 1, beta plus 1 here, it is L to the power beta into 1 over beta plus 1. If we take beta is equal to 0, so it will be here 1, this is 1, this is also 1. Okay, so we take lower limit minus 1, minus L, L is equal to 0, right? L is equal to 0 means this is also 0, this whole thing is 0, this is also 0, this will be 0. So lower limit will not contribute anything. So here you can see this, from here it will be L. So L, if I take common, so it is 1 plus 1 over beta plus 1. I hope you agree with me. So this is what it is written on here. This is constant term, right? I have taken the common LC, that is the 1. Okay, so finally the EMF we are getting, EMF we are getting, EMF we are getting is, let this be here. So EMF we are getting is V0 L whole into 1 plus 1 over beta plus 1. So this is the one. Now look, it is actually proportional to, directly proportional to L. This is true. Okay, this is true. That means the first option. So EMF, change in the flux means EMF, right? Change in the flux means EMF. So it is proportional to the length of the wire projected on the y-axis. That is very true. Okay, now this delta phi remains constant as, like, if the parabolic wire is replaced by a straight wire y is equal to x, and see, if we do that, if this is the one, actually in moving along this way, there is no change in the area, so there will be actually no change in the flux at all. Okay, so in this case the option B is also correct. Option B is also correct. So there will be no change in the area, so flux change will be always constant. Okay, now the option C, if beta is equal to 0, look in this case itself, if beta is equal to 0, if beta is equal to 0, from here EMF, I'll write it here. So EMF, beta is equal to 0, so EMF will be how much? Beta is 0 means this is 1, so it will be actually E is equal to 2 B0 V0 and L. The option says it will be half into B0 V0 L for beta is equal to 0, which is not true. Now we'll see, for beta is equal to 2, what is the EMF? That means change in the flux. So for beta is equal to 2 we get EMF is equal to B0 V0L whole into 1 plus 3. That means it is 4 by 3 V0 V0 and L. So EMF or change in the flux will be 4 by 3 V0 V0 L for beta is equal to 2. So this is also true. So this is how we have to solve this problem. So we'll stop it here for today. We'll take up and solve some more problems from JEE Advanced paper on magnetism and electromagnetic induction part, because there are many questions from induction part in JEE Advanced in every year. So we'll continue in the next class. Okay, thank you for your patience. Bye for today.